Hello everybody, welcome back to part 2 of my Homework 1 Vectorization, Jacobian, Frenet-Serret 3D plotting. I just want to get a really exciting intro in there. Anyway, I'm going to be doing this part 2 section right now. Using closure, explain and code a higher order function that returns functions that calculate the Frenet-Serret tangent and normal vectors for the helical curve. So explain how the radius curvature can be obtained at any point along the helical curve. Okay, sweet. So first off, let's start off by going ahead and talking a little bit about Frenet-Serret. So I believe I just go back here. Yeah, this is the page. So these are the Frenet-Serret formulas. You can see there's 3 of them. I'm just going to be trying to calculate these first 2 in this episode. So I'm looking at the change in t, which is the unit vector of the tangent of the curve, over the change in s, which s is the arc length. And I'm also going to be looking at the change in the normal vector to the curve divided by the change in arc length. So what are the tangent and normal vectors to the curve? Well, if you remember last time, and I just went and combined some of my cells from last time. I haven't made any changes to any of the text or anything like that. But I should be able to run it, and yeah, okay, I get this cell. So this is the curve we generated last time, right? And I want to find the tangent line, which just goes off in this direction. It's tangent to the curve. Remember, tangent is like a line that only intersects at one point along the curve. And then I want to find the normal, which is perpendicular to the curve, and it's actually perpendicular in such a way that it is perpendicular to the tangent, but it's actually the derivative of the tangent. And of course, the tangent is the derivative of the line, if you remember your calculus well. So that's sort of what we're going to be doing. We're going to be taking the derivative of the line, and then taking the second, and then taking another derivative of that derivative. And that's really the main substance what I'm going to do. The tangent is just the derivative of the curve, and the normal is just the derivative of the tangent. But there's a few more things I need to sort of add in there in order to make everything work out. And of course, I want to define it all as functions so that it's callable and easy to work with. So first off, speaking of functions, right now I don't have a function for this curve. I'm just generating some points. So let's go ahead and turn this into a function. So if I define curve, define curve, C-U-R-V-E, and then I want to define that in terms of the time, in terms of the radius, and in terms of the slope in the z direction. I can just go ahead and take x, move it up, take y and z, move it up, and then I'm actually going to say that x, y, z is equal to a numpy array of I need to actually put brackets in there, x and then y and then z, and then I will just go ahead and not hit that. But I will go ahead and return return x, y, z. And so that is my function. Now, of course, I'm going to get an error. Actually, I'm not, because I should be getting an error because x, y, and z are no longer defined, but they're still defined from earlier when I did it. So now I'll just go ahead and say x, comma, y, comma, z is equal to curve, so the function curve at the points t, which is already defined, r, which is already defined, and mz, which I already defined. So now I can go ahead and run it, and ooh, I spelled it wrong. Cruve. That's cool. Nice typo. I have had a really hard time typing today, so we'll see how this goes, but this should all work out. And yeah, now we have the same curve. Everything's defined. I could clear everything, run everything again, and we'd be all good. So now we have now we have this function as a, now we have this line and it's part of a function, so we can call it into other functions. So earlier I talked about the fact that the tangent is the derivative of the curve, right? And so we have a curve. How do we get the tangent? Well, the tangent is the derivative, and the derivative, actually, when you have like a three-dimensional plot with multiple functions, the best way to take the derivative is to create a matrix of the derivatives. So you take the derivative of the first function all the way through relative to each of the independent variables, and then take all the other functions relative to all the other independent variables and build it into a matrix. And this matrix is, of course, what we did last time. It's called the Jacobian. Then you can take the determinant of the Jacobian, even if you wanted to. I don't think we need to in this problem, but we might need to for something else. So, Jacobian Matrix. Feeling good about that, right? So I need to take to get the tangent, I need to take the Jacobian, and I'm just going to go ahead and clear out this so it's not in my way. I need to take the Jacobian of this curve. So how do I get the Jacobian? Well, Jax actually has a Jacobian function built in. It's just Jax.Jacobian, right? I think I did that correctly. If I put a question mark on it, it should give me, yeah, okay. So it gives me just a list of information. So it wants a function. It wants this argnums, which argnums is going to tell it what variable to take the derivative relative to. And then I also need to go back here and look at this allow integer and change that to true so that I can pass certain values into the function. So with that, I'll just go ahead and take the Jacobian of the curve, right? So the curve is the function. The arg nums, let's flush this one out a little bit. Did I get the S? Sometimes I forget to put the S on there and then it gives me an error. It needs to be arg nums. But anyway, let's look up here at curve. So curve has 3 variables in it, right? There is t, r, and slope in the z direction. Well, r and the slope in the z direction are constant, but t changes. So I want to take the derivative relative to t, right? And t is the first variable, which means argnums is going to be 0. It's the first one in this list of variables, which I almost adjusted there. And then I'm going to come up here and I'm going to say that I want to take the, let's see, I need to allow integers. I'm not quite sure why I have to do this or what this means, but if I don't set this to true, then everything breaks. So let's see, doesn't like allow integers. Okay, now it does. So if I go ahead and run this, it gives me a function like I would expect. I'll go ahead and define that as maybe JAC, just for the heck of it. That's what the professor... Actually, you know, I don't like JAC. It's not really descriptive of what it is. This is the curve Jacobian. So I'll just call it curve Jacobian. No, I'll call it curve. I want to spell this correctly. The curve of the Jacobian is going to be equal to that. So, sweet. Now, if I say curve Jacobian of certain values, so I need to give it a t, an r, and an mz, but I don't want to give it just t. That's like this matrix up here, right? Or an array, rather. I want to give it a specific value. So I'll just say when t is equal to 0. I can go ahead and run that, and it returns to me an array. Now this array is actually wrong. I gave it 0 as an integer there. If it doesn't have a decimal point, I need to put a decimal point after to make sure it's a float. So now if I do it, I'll get an error. Oh no. Let's see. It's saying it doesn't like oh, I think it's because, yeah, okay, so these aren't I didn't put these in terms of J and P. So remember last time I imported Jax numpy as J and P. I think all this stuff needs to be J and P's. So now if I run this again, it might let me do it. Okay, sweet. So it returns an array with an x value, a y value, and a z value. And these are the values of the tangent of the derivative, right? So I've got x right here. I've got y right here and z right here. Let's think, does this make sense? So it's saying the derivative at t equals 0, which is this point right here. The derivative in the x direction is going to be 0. Does that make sense? Sure enough, it does. X is sort of this axis right here, right? And as you can see, it's not changing in the x-axis at all in this direction. The y is 3, which makes sense. That's the radius, and that is it's changing all of its direction. Or at least in terms of x, y, it's all in x, none of it's in y right now. As you get like along the curve, it's going to turn some of its x and y velocity into each other, and yeah, tangent is also like velocity, right? It's just the derivative of position. And then you can see this 0.4 back here. That's actually the slope in the z direction, which makes sense that the derivative of z, remember the z function is just the slope times t. And so the derivative of that is just going to be the slope as a constant. So yeah, that's perfect. That's what we were looking for. Now I actually want to put this in terms of a function. So let me go down here and add a little bit of code. Now, if I look up here at the Frenet-Serret, we'll see something that can kind of maybe cause some issues, right? Because it wants the change in the unit vector tangent to the curve, but it wants that change over with respect to arc length, s down here, right? And that's what this is saying. D over ds is the derivative with respect to arc length. So how are we going to get that? Well, if I scroll down here, Wikipedia kind of gives me the answer, which is pretty fun. You know, I like that. But anyway, I go down here. Yeah, okay, cool. So suppose that the curve is given by the this function right here. So this is the function of the curve, where the parameter t is no longer the arc length. The unit vector of t can be written as this. So this is just the tangent t is the position, so the derivative of the position, divided by the magnitude of the derivative of the position. So I can do that, right? Let's go ahead and write that into a function. So I will define this function as big T tangent. I meant to put a big T tangent there, right? And then it needs to be in terms of T, R, and MZ. So that's all good. And I'm going to go ahead and actually copy this down here, right? So this is the tangent function that we calculated up here. I'm going to go ahead and redefine it as tangent curve, because the curve of the tangent is just the Jacobian of the curve. And so I'm going to say that, yeah, v is going to be equal to this tangent curve function at whatever points I specified for the problem. So at t, at r, and at the slope in the z direction. And then I need to take the magnitude. So I'll go ahead and define that as magnitude. And I'm actually going to use Jax's numpy's. I don't know why I'm scrolling up. I'm going to use Jax's numpy's function to get the magnitude. So what is the magnitude even? Does it give me a link down here? It doesn't really. The magnitude is what these two symbols mean. But basically what the magnitude is it's like a... You take all the values, you take like a sum of all the values, and then it's like a sum of the squares, like the values. I think you square them, and then you also like take the square root of them. So there's a way to do it without using this magnitude function, but it's already built in, so let's just go ahead and use it. So it's J and P. I should use J and P. Magnitude is J and P lin-alg, so we're going to its linear algebra library, and it's actually called norm, even though it's not really the norm. It's not the normal. It's just that's what they call the magnitude. I think that's just a different terminology for it. But that's going to be the magnitude of v, which I created here, right? I keep clicking. I need to click Control C. That would be good. And then I can just click v there, and then I will return, right? I will return v divided by the magnitude of v, as defined right there, right? So I go ahead and run that, and I get some values. So let's test this out for a second. Let me take the tangent of, we'll just go ahead and take it at 0, t equals 0, or I'll just leave it 0, and then r, and then mz, slope in the z direction. And, okay, 0, once again, I gave it an integer, not a float. And this is actually the, it's different than, if I didn't do this whole dividing by the magnitude, it would be the same as this. But because I'm dividing by the magnitude, I'm getting the unit vector, and this is relative to arc length. So this is saying that as the arc length changes by a little bit, this is how much the slope and everything else is changing by. So now we've got tangent to the curve, so that's sort of part 1 of part 2. So I guess part 2-1 is this tangent. Now I want to get the normal to the curve. And so I'm going to do something very similar. In fact, it's so similar, I'm just going to go ahead and copy all this, right? And let's go ahead and do the same thing. Take the normal vector, take the derivative of this tangent, because remember earlier when I defined the normal is just the derivative of the tangent, derivative of t with respect to the arc length parameter of the curve. Okay, so I need to take the derivative of the tangent. So I'll go ahead and maybe redefine this as the normal to the curve is the Jacobian of the tangent. So the tangent curve, right? So I'll go ahead and copy this. Actually, no, it's not it's the tangent function. I want to give it a function here. Tangent function. So I'm taking, actually, I want to take this. I'll just copy and paste it over. And I'm making it capital T because I feel like, these are capital T, so I want to name it with a capital T. I don't know if that's really common nomenclature for programmers, but that's what I want to do. And so I'll still use this internal variable v, but v is actually going to be the normal curve at a certain time, at a certain radius, and a certain slope. And then I want to take the magnitude of v, so use Jax's numpy's lineage function and take the normal of v and then return v divided by the magnitude. So if I go ahead and do that, it runs okay. That's sweet. Now if I try to maybe do this, it will give me an error because the name normal, oh shoot, okay, so I need to rename this function as normal, and then I need to run this again to make sure it's defined, because I basically just stole the name from this function over here and defined it as normal. So now I run that, I ran that twice, so it shouldn't really matter. But now I'm getting an array for the normal. But this is the normal vector in terms of arc length, which is a little bit harder to visualize. Let me go ahead and sort of check this by taking the normal vector divided by the, not divided by the magnitude. So I can go ahead and take this normal curve, right? And I'll copy it all over here. And then I want to have this normal curve in terms of, I shouldn't have deleted this, I should have kept it maybe, in terms of, that initial point, right? So it's going to return a device array, and this is basically -1, 0, 0. So it's saying the point normal to the curve at the first point in this chart. So right here, the point normal is -1 in the x direction, and then 0 in the y and z direction. So does that make sense? Well, let's go back here. Normal is always perpendicular to the line, basically pointing towards the central point of the curve. So let's go ahead and let's visualize this for a second. Well, the vector is going to be pointing inside like this. That's what we would expect. We would expect it to start right here and end right here, essentially. And you can see the change in the y direction is going to be 0. The change in the x direction is going to be close to -1, right? Because it's pointing towards the negative x side. But it's fully in the x-axis. And then the change in z is actually going to be 0. Because once again, let's go back up here and think about the z function. We took the first derivative, and it just became the slope. Well, that's just a constant, right? So what's the second derivative? What's the derivative of a constant? The second derivative of a constant is just 0. So, yeah, that's how the slope in the z direction has became 0 in this array down here. So the normal to the curve. So that's pretty sweet. We now have functions for the tangent to the curve and to the normal to the curve. And it's divided by the magnitude, so it's in terms of the change in arc length, which is a little bit harder to visualize, which is why I tried to explain it in terms of the change in time, or t, which isn't really time, I don't think, but whatever. My computer just did something kind of funky. I bumped the connector from my keyboard, so hopefully that didn't mess anything up. But anyway, going back here, this is my professor's video. Sorry, I don't need that. I guess going back here, explain how the radius curvature can be obtained at any point along the helical curve. Well, I've already kind of talked about this a little bit, but just to go back to what we're talking about, we got this n vector, we got this t vector, and when we take the cross product, right, the cross product, we get t, or we get b, which is I guess they're calling it the binomial unit vector. And this n and b vectors are both in a certain plane. And so you can take the magnitude of the cross product of n and b, and when you take the magnitude of that cross product, you're going to get a plane that's perpendicular to this line. And the plane that's perpendicular to this line at any given point can be used to plot points around the line that are used to make this wireframe thing. that we're trying to build. And actually, let me go back. This is just my practice, but if I go and open a notebook, and I'll just get what my professor Carlos gave us, and I'm just really quickly going through here to just see what the final product should look like. And maybe I will connect and run all of them. Run all. Hopefully it'll get going. Eventually it should go ahead and there's the plot we already generated. If I come all the way down here, it doesn't actually give me... Okay, here it is. Yeah, okay. So this is, kind of like the final product of what we're looking for. So as you can see, at any point along the curve, it has a bunch of points around it in a plane that is perpendicular to what we're looking for. So these are all in a plane perpendicular, and they're all sort of just plotted around the curve. So it's pretty cool to look at. You can kind of spin it around. It looks really cool. But I just wanted to go through and show this. I feel like it might be edifying for your understanding of where we're going with this whole function. So I'll go ahead and close that tab. And but yeah, this is what we have for now. Now we have this tangent function and also a normal function. And this is just really going to let us generate like generate a perpendicular plane, which is along the radius curvature. And it's going to be, at perpendicular at any point during the curve. And so that's really going to let us plot all these points. So with all that, I think I'm good for this part of the problem. So thank you very much for watching, and I hope you have a wonderful day. Bye-bye.